Okay, you're good. Thank you all for coming here and being with me. What you heard about things that have happened could not have happened without the help of others, my students who really make things happen, and my wife who's with me today. Is this working? I'm not sure. This is how close I have to be. Okay, this helps, and I want to do it. I'm supposed to talk about problem solving. The particular problem I want to try to solve for you is a new way to stop the spread of viral respiratory infections. Okay, and anybody who wants a copy of this presentation, this is my email address. Okay, you can see it right here, and you write me, and I'll send this to you. Okay. Now, let's begin. The question is, what controls the transmission of viral respiratory diseases? What am I talking about? I'm talking about things like influenza A and SARS-CoV-2, which we call the COVID pandemic that we are living through. So here are two important facts. First, it is transmitted primarily through the air. Now, we didn't know this in the beginning, and you all, I think, have heard at the beginning, people were telling you to wash your hands. I'm all for washing hands, and this goes back to Semmelweis in the medical profession, who learned that helping women with childbirth, it was important to wash your hands. And the medical profession has continued this on. I believe it's true. Okay, but I'm telling you, washing your hands does not stop COVID. Okay, not at all. The other thing is the transmission is from tiny droplets in the air. Okay, not from coughing or sneezing, but also simply by speaking or singing. Okay, a wonderful way to get COVID, get into a chorus. Sorry, this is true. And we know this. We have asymptomatic people who are great spreaders, all this. So we understand this. Now, what else do we know? There are some strategies for reducing viral respiratory infections. Let's go through them. They are keep socially distant from other people. No one knows what the right distance is. And it varies, but we understand better to be farther away. That's number one. Number two, wear a mask. And indeed, wearing a mask really works. We have evidence for this. In my country, unfortunately, this has become a controversial political issue, but I'm telling you, it works. Okay, let's go to the third, which is clean the air in buildings. And people say, how do you clean the air? You do ventilation, or you do filtering, or you do UV irradiation. Now, the UV irradiation works, but it's hard to UV irradiate this room, right? You don't want to do that. And there's a lot of emphasis this way of what's going on. This is what presently people say, right? But I will argue, I'm going to argue to you that this approach ignores another important fact, namely the transmission of viral respiratory infections is seasonal. People already speak about the flu season, but they don't pay attention as to what's causing the flu or other things to be seasonal, to vary with the seasons. First, we have to convince ourselves something about this. I hope to convince you that this seasonality correlates with relative humidity in the air. Humidity, how much water it holds. And I'll be talking about the percentage of water at a certain temperature of the air and trying to show you something about this. This is what relative humidity is about. Finally, I will offer a possible explanation for this behavior. Because there hasn't been an explanation, by and large, people have paid no attention to this. Let's begin by convincing ourselves about seasonality. Here's data from Paris, France, collected over the years you're seeing here. let's take a look. Okay, come on, move. Okay, here we go. That's 212 all the way to 215. And we're looking at what? We're looking at a whole bunch of different viral respiratory diseases, from influenza to coronavirus. And what are we seeing? In the white part is the summertime, and in the shaded light blue part is the wintertime. And it's pretty clear it's seasonal for all of them. And now let's go look some more. Here is very recent data. This was posted September the 16th, 2022. So therefore, it's unlikely you've seen this before. It's not yet even published. It's going to be published. Okay. And this is the most recent COVID case rate. And it's per million, et cetera. And I want to show you, if I can, what's happening. I got to bring this closer to me so I can see it. Okay. Somewhere there's Greece. Come on, I want to find it. That's Germany. Come on, where's Greece? Go up. There's Greece. Okay, and the point I'm trying to make to you is Greece is really sort of no different than a lot of other countries. And what you find, and these are the months of the year, and it's very clear, this is the scale, that it's really worse in the wintertime and pretty much goes away in the summertime. Now, there's fluctuations and there are mutations in the virus that we know. And this is the cases for COVID. What about flu? Here's the pre-pandemic flu. Same answer, even clearer. Okay, this is now endemic. We know that. So I hope at this point you are convinced that this is seasonal. Okay, what? This is the time series comparing the FluNet data on seasonal influenza. There's always somebody who asks me, okay, that's the northern hemisphere, but what about the southern hemisphere? And guess what? It's completely out of phase. Okay, as shown here. Once again, summertime, wintertime, doesn't matter whether you're sitting in Argentina, okay, one side, or you're sitting in Canada, same effect, okay? And this is so. And so now you should believe it. So the claim I'm making to you is little attention has been paid to seasonal variation of viral respiratory infections. And here's a quote that I found sort of arresting. This is by some people at the Bill and Melinda Gates Foundation, Scott Dowell, who I don't know. And I'm going to read you this quote. If we knew what suppressed influenza to summertime levels, that would be a lot more effective than any of the flu vaccines we have. Oh, that's interesting, isn't it? Oh, I think, okay, so we want to see if we can understand this. I want to give you an understanding. The first thing I want to explain to you is that we as human beings have been moving away from nature in the following way. About 2,000 years ago, everybody lived outdoors. People lived in tents, okay? People were exposed to the outdoors. What's happened since is that we now spend about 90% of our time, like we do right now, indoors. And we do that in the summertime and we do that in the wintertime. And we have become homo indorus, okay? Very much. And moreover, as time has gone on, we now go to places that are airtight and mechanically ventilated buildings. It's going to be important, I'm telling you. We've really moved away. And we've also moved out of the sunlight, another matter to make to you, to other type of lighting like we have right here, which actually, if you look at it, is not giving you the full spectrum that you get from sunlight, okay? It's cutting off UV, it's cutting off IR in general, okay? So how can outside temperature influence seasonal variations of sickness? To begin with, the virus doesn't care that much about the temperature unless you get so hot that you denature it. You're not that hot, okay? Sorry, you're not that hot. So what's going on? What's happening? And the answer starts to be the following, that it really seems to track strongly the relative humidity. And I'll show you this. This is data from Gothenburg, Sweden, but I can give you lots more data, the same sort. And this is showing you, see, January, February, March, these are the months of the year. And this is showing you the red is the temperature. And being Sweden, it goes below 0. Okay, it's centigrade. And the blue here is the relative humidity. And we see that the relative humidity goes down in February, okay? And it goes up in August, okay? And it seems to vary from around less than 20, around 25% to around 50%. And why? Because in the wintertime, we keep warm by heating the air of our buildings to keep us warm. And that dries them out. So the relative humidity percentage goes down. Got a sense of this now? And it's clear how that's so. Okay. What am I showing you? Sum of weekly new confirmed COVID-19 cases per 1 million people across the 5 representative countries, Canada, Germany, India, Ethiopia, and Chile for this period, okay, is a function of weekly specific humidity. And once again, notice, I mean, it's pretty clear. If you really make the okay, you make the humidity, you're getting this type of shape, okay? If you get the small relative humidity or specific humidity, your cases go way up. And there's some sweet spot in between, which we're going to try to understand. Okay, very interesting. This is data. The data has been published. I forget what year this is. I'll have to stick my head in and look. When was this published? I don't think it says, but it's very recent, but still no one's paying attention to it, okay, as to what it means. And I'm showing you yet more stuff. And I think at this point, hopefully you're convinced. I'm showing you the relative humidity here, and I'm showing you the cases in New York and in Texas, I think it is, of flu. And wow, it's striking. You look at the data. I hope you see this. Okay. Okay. And another data. And I'm showing you there's a really good spot between 40% and 60%. That's where you get minimums. And that's on hospital data. Okay. And we all know about the droplets and about how far they travel and that they dry out. And if the relative humidity is really low, they dry out quickly. The virus gets desiccated. Okay. And it's sort of dormant, but it floats around, small, stays in the air. Okay. And that's bad. Okay. Somehow, if we can keep the relative humidity at the right level, it'll stay as a droplet much longer. And I'm going to show you that that matters since it's being carried by droplets. Okay, and we'll get to that. So here's now the humidity-dependent decay of viruses. This is beautiful work done by Lindsay Marr at Virginia Tech. And she's showing this very interesting U-shape versus relative humidity, what you've seen before already. But bacteria are different, okay, than viruses. And here's the findings of this study. Survival of bacteria increases as relative humidity values increase. It is thought that increasing evaporation increases salt concentration of the droplet and kills the bacteria by osmotic pressure and stuff like this. But doesn't affect virus. That's what happens to bacteria, but that's not true of viruses. Survival of viruses has a U-shape, a V-shape, doing better at higher or lower relative humidity, but worse at intermediate relative humidity values. This is a fact, again published. And she writes, the mechanism underlying the relationship has not been explained, particularly for viruses. Okay. And what do I have here? Here is indoor humidity of dwelling and association with building characteristics. And this is behavior and health in a northern climate. Let's look again. I'm having trouble. See if I can do it better. The year of this, okay. When is it? 2021. Again, I'm showing you very recent data. Okay. And what do they say? Analysis shows that low indoor relative humidity is a realistic issue in Swedish dwellings during the heating season. The issue is more prevalent in apartments with single-family houses. In addition, low indoor relative humidity seems to be more extensive in dwellings with higher indoor temperatures, smaller volumes, higher ventilation rates. Notice ventilation is not helping you here. It's actually hurting you. And frequent airing practices, lower number of occupants constructed mainly after 1985 in city suburbs in the northern parts of the country. The analysis offers additional evidence to the scientific literature for possible correlation of low relative immunity with specific health symptoms, complaints, and disturbances. And I hope I'm trying to make it so you really realize this. Okay, relative humidity is really mattering here, okay, in some way, and yet not paying much attention to it. So how long the coronavirus survives in the air depends on relative humidity. And I don't think I'm going to bother you too much more by reading this type of stuff to you. You can look at it. Another study. This is a study that has been published when? 2022. Okay. July 7th, 2022. We really see this, what's happening. And I want to offer a different possible explanation that can explain this behavior for viruses. So I'm going to give you now an idea of what's happening, if I might, my idea of what's happening. And I'm going to make a claim to you. First claim, water microdroplets, small droplets, contain reactive oxygen species, ROS, unlike bulk water. Bulk water, inert, benign, great solvent. Little water droplets, I'm going to try to convince you, are highly reactive. And, okay, and very different. And I want to now first, by giving you visual proof, the first proof I want to give you is that little water droplets generate hydrogen peroxide. Some of you recognize hydrogen peroxide in bleaching hair, or people gargle with it. It's a disinfectant, right? It's reactive, okay? And here's a species that I'm showing you. This can be synthesized, and indeed first synthesized at Berkeley by these people, made in my lab by Catherine Walker, who since graduated. And notice this carbon-boron bonds. We're not going to do chemistry today. This is actually clipped off by hydrogen peroxide, breaks these bonds, leaves this molecule, which some of you will recognize as something called fluorescein, which easily fluoresces, okay? And we're going to take advantage of that. I need a name for this. It has an IUPAC name. That's hopeless, okay? We're going to call it PF1, okay? And I want to show you if we take 10 micromolar PF1 in bulk water. I'm putting it in bulk water, and I'm showing you the dark field image, bright field image, pardon me, and the fluorescence spectrum. And, you know, I don't see any fluorescence. I don't know about you. And I'm showing you now air-water interface in a beaker. And look, it's still dark. Nothing happens, okay? But what happens if I make water droplets? They light up, okay? Of course, by diffusion, it goes throughout the droplet. But I'm telling you, it's really happening at the surface. And here it is in bright field. We see the droplet, and here it is a fluorescence spectrum. And we're shining laser in and getting light to come out. I don't have to explain fluorescence, I hope. And so I want to now get the idea of how this depends on droplet size. This is going to be important, and why this has been missed before. So let's look at this. We're going to now do confocal microscopy and look at these droplets. And this is a fluorescence image of spontaneous generation of hydrogen peroxide in aqueous microdroplets. Okay, and we can use a microscope to look at it all. And what do we see? Pay attention to this, if you will. Here are 3 droplets, A, B, and C. Well, what are they? A is 150 microns. A has the width approximately of a human hair. Okay? Human hair about 100 microns. Okay, B is about 50 microns, half a human hair. And C is 16 microns, a very easy number to get with droplets. Okay? And what are we seeing? If we only cut the lights down, you'd see it. That A, hardly any fluorescence. B, there's just a hint of green. But C lights up. And really, small droplets make this happen. There's just no question, okay? And you need small droplets to make this effect, and that's shown in this graph to the right. Um, okay, and I think next what I'm going to try to do, and I may need your help again, Theo. I need to turn off the pointer so that I can actually show the video. Can you do that for me? I'm sorry to. Let's get rid of the pointer because it won't allow me to otherwise to show the video. I don't know why, but it won't. Okay. Now, here is work with J.Q. Lee primarily, who's now at Seoul National University in Seoul, Korea, who was some postdoc with me and other people. And I want to show you the production of hydrogen peroxide. Come on back. Okay. What we're going to do, come on, where's, here we go. We're going to play the movie. Here we go. And what we have is a peroxide test strip. It has an enzyme called horseradish peroxidase and a dye. And if it just sees water, nothing happens. But if you send hydrogen peroxide in, it will turn blue. Well, you can't maybe see it because the lights aren't out. But there's really hope. Is there any way of killing these lights in front that would help? But anyways, here it is. And if you look carefully, I tell you in time, this thing will turn blue. Can you start to see it turn blue? Okay. And notice no electric fields being applied. All this is oh, come on back. All this is air or nitrogen blowing past a little capillary that has water to make the droplets come out. It's like a perfume bottle. Okay. It squirts it out, making small droplets. And you see it, that there's really hydrogen peroxide being made by small droplets. I tried to publish this. I just thought I'd tell you. I sent this into Nature because I was so excited about this result. I mean, who would believe, and that was the trouble, who would believe that little water droplets are making hydrogen peroxide? There's no hydrogen peroxide in normal water. It's all H2O. And I'm telling you about HOOH. Okay, wow. And I got nowhere because the referees who came back, some said this is unbelievably exciting, and others said this was unbelievable. And the editor is conservative, and she told me, Magdalena Helmer, she said, if this is, people have been studying aerosols, she said, for years. If this were true, it would have been seen already. And that type of argument is not, from my viewpoint, a scientific argument, but it was deadly. I couldn't publish, so we went on elsewhere. And where does the hydrogen peroxide come from? I think it's coming from the recombination of the hydroxide radical, OH, in water. Now, water we know makes H plus and OH minus, but I'm telling you there's OH in little droplets, okay? And so we postulate that the H2O2 originates from the recombination of the OH radical floating around in water, okay? And do we have any evidence for hydroxyl radicals in water microdroplets? And the answer is absolutely yes. And I'm showing you, here is something, salicylic acid, the type of thing you find in the aspirin. OH goes on to make some other compounds that are written here. And sure enough, we see them, that it really scavenges the OH. Here's another example. We spray this itself, and the OH goes to water with this H3O plus and forms these compounds that are H2O4 plus, which we can see with a mass spectrometer. And we really see it. And these are published. Notice the date again, 2022. This very current work that I'm explaining to you about. And so this is the capture of hydroxyl radicals by hydronium cations in water microdroplets. And the OH is coming from something. Okay, it's there. And now I say that they're recombining. There have been people who've criticized all this. There's a publication that comes from KAUST by this group that says, well, it's all due to ozone in the air that somehow reacts. And sure enough, ozone will go on to make OH or hydrogen peroxide. And so it produced a great deal of worry on our part. These people in my group Masood Mirgardi and Muhammad Mofidfar, okay, and I worked on trying to see whether or not we could generate hydrogen peroxide spontaneously in water by itself, okay? And this is, again, published in 2022 recently, okay? And here's our setup. We have O2 or N2 or different nebulizing gases. We pass them through water, as shown here, right? That tends to remove anything. We then actually add an ozone scrubber to try to take out any ozone that might remain. And we put them into a sealed chamber, spray in distilled water, control the water very carefully. Then collect it. We have an ozone meter to know whether or not there's any ozone. And we then collect the droplets and we run nuclear magnetic resonance, NMR. And sure enough, we see that there's hydrogen peroxide, okay? We can add it or we can show it in the red, what's there, and we get a feeling for how much is being made. And it's really happening spontaneously, okay, from the droplets. And we find out that if we change our gas from 99.999% pure nitrogen, which costs a lot of money, okay, we did that to try to be sure, to adding air, to adding much more oxygen, okay, to adding pure oxygen, it actually goes up. So oxygen itself, there is an interaction of gas with the droplet, but that's not the primary source. Show you what is. Here is an example of, again, work published 2022, in which we look at something that fluoresces with hydrogen peroxide, and we see that just glass and water in contact make this fluorescence. Can you see the fluorescence here? It's orange compared to here. It's diffusing in, it's being made on the walls. So there's really a contact between water and silica that can actually make hydrogen, make the OH, which goes on to make hydrogen peroxide. And some of you might be familiar with something that's often done in physics, particularly. They make take a rod and they take some type of cloth and rub it across it and then have it all charged up. You don't actually have to rub, just contact will do it. It's called contact electrification. And that's what's going on, and it's complicated. So here, I'm going to call it aqua ROS. It's water that has this reactive oxygen species. And I'm going to tell you it acts as a disinfectant. And here's the publication again for this from people in my group. Okay. And here are the workers. Now we're teaming up with people like Denise Monak, who's taught it. She's a virologist who's taught us how to do colony counting, and very much inspired in this work by Adrian Davica and Sinisa Vukovic, who indeed urged me to look at this as to what it might have in terms of health consequences. Got me interested in this. And here's the overview. You just sending in water, very simple. And we're going to spray the water to make little droplets. And I'm showing you that it kills 98% of E. coli and salmonella as well. Okay. And we've tried it on spinach. It also cleans up spinach. And this is amazing. It's a disinfectant, little water droplets. And we're trying to get people to pay attention to this. And how does it do it? Well, the reactive oxygen species actually break down the walls. They gobbles them up, okay? OHs are really strong material here. And the next claim is that hydrogen peroxide production in water microdroplets sprayed in air depends on the relative humidity of the air. Oh, this now starts to tie things together. And here's again our publication of this work, okay? And I'm showing you our data. We're talking about in milligrams per, milligrams per liter of H2O2, and we're going from 2 to about over 6, from about 23% relative humidity to about 53% relative humidity. So a small change in relative humidity really helps this thing happen. And as I was mentioning, the droplet will also stay around longer, and this will eat up the viruses. So we're getting to now have an understanding of this. I also want to very much convince you of the universality of H2O2 spontaneous generation at water-solid interfaces. Here are a bunch of metal oxides, Here are stuff involving what's called PM 2.5, particulate matter of a certain small size. And in all the cases, we find hydrogen peroxides being generated at the surface. And it's through this contact electrification. This really may help change the modeling of what aerosols are like and the chemistry behind them. And I hope this is giving you some idea now. So I reached some conclusions, if I might. First, the variation of reactive oxygen species with the percentage relative humidity of the air helps to explain why 40 to 6% relative humidity is most healthy and why there's been a seasonal variation in the transmission of viral respiratory diseases. We need to change a paradigm from cleaning the air, okay, to reducing the reducing the load of alive viruses in the air, and we want to think about the possibility of doing that by controlling relative humidity. And this change calls for a new strategy that pays attention to include proper lighting, because it turns out, if you don't have time to tell you, that even radiation helps this process to go on further to form OH, okay? And setting the proper percentage relative humidity for indoor air in buildings, as well as cleaning the air. And if I might, let's again talk about public health implications. So what's the worst place you can go to get a viral respiratory disease? And I'm telling you, it's in an airplane. Why? They say, oh, they boast, we turn over the air so many times. They do. But the relative humidity in an airplane is about 5%. That's why they serve you water all the time on airplanes if you make long trips. I know, I came here from the States, okay? And you also sit in the dark. All the wrong things. And yet there's a simple device called a humidifier, which could help fix this problem. But we got to get people to think about this. So at this point, I think I should stop. And I think now you understand why I'm so excited by water microdroplets. Thank you all for coming to hear me speak. You go ahead. Sit down. Okay, sit down.
Ακολουθεί μουσικό πρόγραμμα με τον κύριο Ορέστη Κουσαθανά. Ο κύριος Ορέστης Κουσαθανάς είναι φοιτητής του Τμήματος Χημείας και διευθύνει την χοροδία του Πανεπιστημίου Κρήτης. Σήμερα θα μας παρουσιάσει ένα μουσικό ταξίδι από τον Ερετόκριτο μέχρι το σύγχρονο τζάζ.